Welcome everyone to this course CBS VLSI design. In today's class, we are going to learn about data path and controller synthesis in high level synthesis. So, let us again look into this high level synthesis flow. So, if we have already seen that high level synthesis consists of preprocessing, scheduling, allocation, binding, data path and controller generation, and then finally we will get the RTL, right. So, we have already have discussed about this scheduling and also allocation binding. So, scheduling assign the operations to timestamps. So, we understand which operation is going to execute in which timestamp, and then allocation and binding actually identify the number of register needed and how these variables get mapped to registers, how many FUs needed and how the operations are getting mapped to FUs, right. So, after this allocation and binding, we already have that information with us. So, we know how many registers are there and how many FUs are there and exactly how the operations or variables are mapped to them, that is also known to know. So, the next phase is data path and controller generation. So, in this step, so we have to make the connection from this register to FUs, right, because I know this operation is going to happen in FU and the data should come from registers. So, you have to make the connections from register to FUs, and also once the operation is done in the FU, that data has to go back and back to be returned to the registers. So, this is what is the interconnections, and that is what is the data path synthesis. So, based on this interconnection requirement, you try to make the connections, right. So, obviously, once you try to make the connections, your objective will be to use optimize the interconnection cost. So, we will come into that point, what is the interconnection cost and how to optimize it, but the overall idea is that. Okay. So, once the connection is also made, right. So, then the controller generation comes. So, we already know how many states are needed to execute the behavior. So, we know the FSM states and the transitions, right. So, this is also known. So, that what are the states needed and what is the transition. So, these are all known to me. So, what is this controller FSM does, because this data path is going to execute this behavior now, and this data path interconnections are basically time division multiplexed. So, we have to make sure that in every clock, so suppose you are in clock 1, the operation to be executed in operation time step 1 is going to happen in the data path, right. So, that is something you have to make by the controller. So, based on that, it has to assign some proper control signals to this interconnection units and also to the registers enable, right. So, these are the control signals you have to assign appropriate to the operation that is scheduled in that state, right. So, based on that, this controller will identify how many minimum control signals is needed and what is the value of those control signals in every time step, right. So, that is what is the controller FSM. So, basically here it will just identify the value of these control signals and so on, right. So, this is what is the controller synthesis. So, once you get both, your final RTL is ready, right. So, this is your final RTL. It consists of a data path and a controller, and they actually do a handshaking. They this controller generate the control signals for the data path to perform operations, and the data path gives some status signal based on which the state transition actually happen in the controller FSM. Okay. So, this is what is the high level synthesis flow. In today's class, we are going to learn about this phase. Okay. So, let us move on. So, as I mentioned in the previous slide that after scheduling, we know in every time step what operation is going to happen. So, this is my schedule information. After register allocation and binding, we will know how many registers are needed and what is the mapping of the variable to the registers, and after FU allocation and binding, we know how many FUs we need and what are the operation is going to map to each FU, right. So, this information is there. So, now we can combine this and we can get the RTL behavior. Okay. What I can do, I can rewrite my schedule behavior, which is schedule behavior, which I can combine this allocation and binding information, and then I will get the register transfer level behavior. How? What is there? So, in every time step, so in the time step 1, there is a operation T1 is U into dx, right. So, what T1 stored in the hardware, it is R1. So, I can replace this by R1, this U stored in R5. So, I can replace this by R5, dx stored in R7. So, I can replace by this R7, and this operation 1 is actually mapped into V1 is mapped to operation mult 1. So, I can replace this multiplier by mul to 1, right. So, this is my register transfer level behavior. So, this way I can replace all the operations by the corresponding registers and the FUs, and I will get this behavior, right. So, this is what is called RTL behavior. So, here it is the transfer of register values, the behavior is represented using the transfer of register values, that is why it is the RTL behavior. So, here it is just given as the operations, but you have to realize this RTL behavior using a data path, and that is what we are going to get in this data path synthesis diagram. So, we want to get a data path that we are going to realize this RTL behavior, which is written as a text file. Okay. So, now let us understand what is this data path interconnection synthesis problem. As I mentioned, so we already know that these are the operation is going to happen in time step 1 in the register transfer level, these are the operations going to happen in the time step 2 in the register transfer level, and so on. So, you might have many state, I am just taking 2 state for explanation purpose. Okay. So, what you can do for each FU, you can identify what are the inputs, possible inputs to this FU in overall all time stamp, right. So, if you just think about M1, so for M1, so suppose this is your FU M1, which is a multiplier 1. So, in time stamp 1, R5 will come here, right. So, R5 will come here and R7 will come here, right. So, this is in time stamp 1. In time stamp 2, this is again M1 and R1 will come here, right. So, this is R1 will come here in time stamp 2, and here it will R2, right, in 2. So, this how if here I have taken only 2 state, but if suppose there are 20 states. So, every time stamp you can identify the inputs of that FU over all time stamp, right. So, if you just do this for each FU, you will get such behavior, right. So, you will understand these are the possible values of input. So, this may be in time stamp 1, 2, so 3, 4, 5, 1, 2, 3, 4, 5, and this is the output, right. So, 1, 2, 3, 4, 5. In the previous behavior, what I have not done is basically this will go to multiple places, right. So, this is updating R1 in the time stamp 1, this is updating in time stamp 1, and this is updating R2 in time stamp 2, right. So, you will identify all the possible inputs for the FUs and what are the possible outputs of this FUs, and they are actually time division multiplex. It is not that all are coming in the same clock, they will come in different time stamp, right. So, this information you can gather from this RTL behavior, and this is what does it mean. I have to make connections from this R1, R2 and this register to the left input of this, right. And similarly, I have to make connections from these registers to the right input of this FU. I have to make connection from this FU output to those registers, such that every clock I have to give proper control signal, so that that particular operation can happen. Okay. So, make the connections, there are 2 possibilities. So, the possible data path interconnections are bus based architecture and mux based architecture. Let us understand that. So, in the mux based architecture, which is multiplexer based architecture, so you have the FU, right, and you have the set of registers, you know these things, right. So, this is given, and I know what are the inputs should come to the UNU. So, you add a multiplexer here just to multiplex the input. So, in the previous example, if you take for this FU, right, you put a multiplexer at the left input, you put a this is a multiplexer. So, you put a multiplexer at each input of the each FU, right, and then you have R1, R2, R1, R5, R4, right. And then you need a, so there are 5 inputs. So, you need kind of 3 bits control signal, right. So, there are 3 bits control signal, and similarly here you also put 5 inputs. Basically, this is 0 0 0, this is 0 1 0, this is 1 0 sorry 0 1 1, this is 1 0 0, this is 1 0 1 say, and similar to this. So, here you are putting R6, R1, R5, R6 and R2. So, and again you need a 3-bit control signal, and then in the first clock you give 0 0 0, right, and here also you give 0 0 0, right. So, you give 0 0 0 here, here you need to give 0 0 0, and similarly this output is going to this. So, basically this it will go to all these registers. So, there should be some enable signal to the registers, and there should be a marks at the input of the register, because I just talked about one FU, but it may be that the input to the register can come from multiple FU. So, you have to put a multiplexers at the input of the registers also, right. So, that is what this marks based architecture. So, you have this multiplexers at the input of the FUs, you have multiplexer at the input of the registers, because the register input can come from many FUs, and to the input of the ALU can also come from many registers. Okay. So, this is why you have to put these multiplexers, and then you have to give appropriate control, you have to assign control signals, and you have to make sure that the operation that has to be executed in that particular control step, you give that corresponding control signal, then things will happen, right. So, for example, suppose you have this is say R1, let me just complete this diagram. So, R2, R3, sorry, this is R7 and this is R4, and let us assume there is a marks at the input of this registers, right, and this is one of the input to this. So, since I have only taken one FU, so I am just making one connection, there may be some other FUs, right. For that FU the other connection will come, and also there will be some enable signal. It may be that in some state you do not want to update one register at all, right. So, you need some enable signal as well. Okay. So, now suppose you give and say this is so this is a single bit, and this is 0 1 0 1 0 1 0 1, this is 0 1. Okay. So, just for simplicity I assume that. So, now in the first control step in CS1 in timestamp 1, because I want to put R1 here, R6 here and R1 here. So, the operation is actually R1 equal to R1 whatever the operation into R6, right. This is going to happen. So, if you put 0 0 0 here, so this R1 will come to this place. If you put 0 0 0 control signal, this R6 will come here, and since you give a 0 here, so this will basically go to this register, right. So, and you have to give the enable equal to 1, other enable is 0, right. So, if you do this particular register operation will do R1 equal to R1 of R6, that is the operation is expected, right. So, in the timestamp 1 you should give 0 1 0 here, sorry, this will be 0 0 1, I mean you understand that, and here you have to give 0 here and others will be 0, right. So, if you give that, it will do R1 equal to R2 plus R1. So, R2 operator R1. So, this is how the connections will happen, right. This is what is marks based architecture, that you take you put marks at the inputs of the registers as well as the FUs, and based on the connection requirement you put the control signals, and during the generation of the controller FSM you give the assign the proper control signal, so that the expected operation is going to happen in that FUs. Okay. The alternative architecture is called bus based architecture. Okay. In the bus based architecture, we are not making any multiplexers. So, what we are doing? We are taking a fixed set of bus. Okay. So, we are going to take fixed set of buses, and the bus we are going to connect these registers and the FUs based on the connections. So, basically if in the one bus, if I connect say this R1, and then there will be a switch here. Okay. So, that if the switch is on, then this data this bus will take, and say I have also connected R6 to this bus 1. Okay. So, that means if I put this value 0 and this is 1, then R5 value will come to bus 1, right. If I put this is 0, this is 1, then this R1 value will come to this bus. Okay. So, you cannot put more than one at a time step, then it is a rest condition. There are two data coming to the same bus, so it will be unstable situation, right. So, you can and in a control step only one of the input can give the data. Okay. Similarly, if this R1 needs to transfer to this ALU1, so I will make a connection from this bus to this, and I will put a switch. and say from this bus 1, say I want to make connection to this ALU 2 also, I will make a connection like this and I will put a switch here. And then what is going to happen? So, in say timestamp 1, say if I put this 1 also, that means, and say this is 1. So, what is going to happen? This R1 will come here and then from this switch it will come to this. So, the left input of this FU will be R1. Similarly, since this R2 is also coming to this switch and this bus, so R2 can come here and this is also connected here. So, suppose I put this control signal equal to and 1, this control signal 1. So, then R2 will come through this line to this ALU, right. So, this way, so that means R1 of R2 is going to happen, right. And similarly, at the input of the register also we need to add some buses, and this FU will be connected to this and there will be switch. So, every connection is basically switch and this register also switch, and say suppose I want to put this data into say R3. So, what I am going to do? I am going to put this equal to 1 and this equal to 1. So, that means this output of this FU1 will come through this line, you will come here and through this you will go to R3, right. So, then it is basically R3. So, this is how I can make the connections, and I will add the switch in every places, and then I want to make sure that in the every time step, based on the transfer required, the actual RTO operations, I am going to set the bus signal to 1, and as a result the corresponding register input will come to the FU, and based on the destination address, based on the destination register, I am going to make the switch connection accordingly. So, that the output of the FU will go to the actual registers, right. So, this is what is the bus based connections. Here obviously idea is that you use minimum number of such switch, because you cannot add all switches, then it is too much of switch and cost. So, you have to make sure that you first determine how many minimum buses is needed, and for each FU input what are the line it should be connected. So, you have to identify the minimum number of buses and minimum number of switch for each component. For each register, what is the bus it needs to be connected, you identify the minimum such occurrences, right. Similarly, for each FU it has to connect it to how many, what is the minimum number of buses it needs to be connected. Similarly, the output of the FU, it can be connected to both or it can be connected only one based on the requirement. So, your optimization objective is to identify the minimum number of buses and minimum number of switches. Okay. So, that is the optimization objective, whereas here your optimization objective is to identify the minimum number of muxes. What is the minimum number of muxes needed, that is the optimization objective. We will discuss this in detail in this class. So, we understand this. So, we have already explained this for these connections what is this mux based connection. So, I can actually explain again for this what is the bus based connection. So, say suppose you have a FU here, right. So, this is your FU, right, and your register say R1, R2, R3, R4, R5, R6, right, R7, and suppose, so basically here you know you have to execute R1 equal to R1 operator whatever the FU, suppose this is plus, so it will be plus R6, right. So, suppose there are 3 buses here, right. So, to make sure I have to make this R1 connection. So, I can make a switch here, so that this will come to bus 1, and I have to also make a switch here. So, that this R1 will come here. Similarly, R6 you need. So, you cannot put into this bus, because in the first time step you need this data. So, this R6 must be connected to the other bus, and similarly you need a connection here as well. So, then if you put 1 and 1 here, 1 and 1 here. So, this data R6 will come here. Suppose there are 2 buses here as well, okay, and this FU is connected here, and the output should go to R1. So, what is going to happen? This must be connected to one of the bus, and from there there will be a connection here, and if you put it 1 and 1 here. So, then this so in this time step this R1 plus R6 equal to R1 equal to R1 plus R6 is going to happen, and the next time step the operation is R2 equal to R2 plus R1, right. So, that means here you need R2 at this input. So, what we can do from R2, say suppose you make a connection here, you make a connection here and you make a 1 here, and then this will come here, right. So, then in the next step you put this 0, so that only this R2 will come here, and from R1 you make another connection here and you put it 1 here, 1 here. So, this will come on here. So, through this bus R1 will come here, and through second bus R2 will come here, and this output should go into R2. So, I can put again a switch here which is already there. So, I can put 1 here and 1 here. So, then this output now, and this is 0 now. So, then this output will come through this, right. So, this is how I am going to make the connections. As I have already explained that here the objective will be to identify what is the minimum number of buses and how to assign this variable to these buses, so that there is no overlap or contradiction, and the use of bus is minimum, right. So, that is something is the objective during bus based interconnection generation. Okay. So, for this example I will just try to show you how the mux based connections happen very quickly. So, we have already discussed that from this, if I combine this and this, if I combine this and this, I will get this RTL behavior, right, that I have already discussed. And suppose I have this RTL behavior is with me now, and I have to make the connections, the mux based connections. So, here this FUs are there are 5 FUs, and these are the 11 registers, and I have to put basically mux here, right. So, I have to put mux here because there are many operations can come here, and you have to put a mux at the input of the registers, right. So, we have to put mux here. So, let us see for operation 1. So, R1 should come here. So, R1 will come to this FU, and then sorry R5 will come to the FU. So, this R1 will come here. So, this is a fixed line, and in the next time step R1 will come, right. So, what you have to do is basically there is a mux you have to put here. In the first time step you need R5, and next time step you need R1. So, this will be a multiplex between R5 and R1. At the right hand input it is a multiplex between R7 and R2. So, I am putting R7 here and R2 here. So, this is a multiplexing between R7 and R2. At the output this will go to R1 and this will go to R2, right. So, they will be connected. So, now for this mux how I will decide? I will see one R1. So, this R1 is coming from M1, right, and in this time step R1 is coming from M2. So, there will be a mux here, and one of the input will be from M1 and other input is from M2, right. So, this is how the connections will be decided. For R2 here it is coming from M2 and here it is coming from M1, right. So, again there is a mux you have to place at the input of R2, and there will be 2 lines, one is from M1 and one is from function unit M2, right. So, this is how you have to see for each time stamp what are the possible inputs are coming, and based on that you put a mux here, and for each register's input you see how many so for every time step what are the FU from which the inputs are coming, and based on that you have to put the muxes here. And if you do this for all steps you will get some connection like this. So, here I have just shown for 2 FUs. You can do all rest of the things. I am not completing the whole complete discussion, but if you just complete this for complete behavior you will get a connection like this. So, this I got this. So, you can see here we need a mux where the control signal will be 1 bit. It is 1 bit, it is 1 bit, but here it is 2 bit. It is 2 bit because there are 4 possible inputs. Okay. Here there is no mux needed because this only one variable is coming all the time. Okay. And similarly, here we need a mux of size 2, and this is a direct connections, we did not need any mux. Okay. So, based on this connection requirement you can identify these interconnections and identify the mux sizes. Okay. So, this is what is all about. So, for this bus base, if you just take the same behavior I have already explained. So, you have to identify the bus, the minimum number of buses that I have already explained, and also the switches, because there are many registers here, right. So, there are many registers here. I can connect this register to all switches and I can put switch there, but then I need if there are say 4 registers and 3 buses, I need 12 switches. which is something may not be needed, because this will give you the maximum flexibility that when any register value can go to any bus, but you may not need that much of flexibility. So, it is a basically maximum possible interconnections things. So, I do not need that. So, probably by analyzing this behavior, what I understand, say probably I do not need this switch, or I do not need this switch, I do not need this switch, say probably, right. So, probably I do not need this switch, and then say I do not need this switch, or say this switch, right, and so on. So, this is the final connection set. Similarly, for FUs, you can connect this all input to all switches, right. So, then if the number of FU is say k number of our FUs and say n number of buses, so it is k into n into 2, right. This is the number of switches you need. Again, when we can show that this number of switches is too much, so you do not need that, right. So, you can actually remove some of the switches, right. So, you can remove say some of the switches, right. So, you can remove some of the switches. So, suppose you do not need this switch, you do not need this switch, you do not need, and so on. So, this can be determined by the this RTL behavior, right. So, what are the operations going to happen. So, this so if we try to summarize this data path synthesis bus based architecture binding problem. So, your first problem is basically you identify the minimum number of buses first. What is the minimum number of buses needed to accommodate all this? So, this is the first requirement. So, the bus to make the inputs, and you need also bus here for the register inputs, right. So, this is the input to the FUs, this is the register input to the registers. So, you identify the minimum number of buses to accommodate all the data transfer, right. So, that is the problem 1, and you can actually have another problem that you given a fixed number of buses, right. So, say suppose somebody tell you that there are 4 buses at the input of the FUs, okay. So, you have 4 buses here. So, then your objective could be that for each buses you try to put the maximum number of data transfers, right. So, so you have given 4 buses, and then so there are maybe say 100 data transfers. So, where all these 100 cannot be placed here, right. So, for example, 50 can be maximum place here. So, you identify what is the maximum number of data transfer can be placed into these buses based on the requirement, okay. So, this is what is the problem here, right. So, this problem can be formulated again as a ILP formulation. So, I will talk about this ILP formulation briefly. So, it says it is basically similar to this port assignment problem, okay. So, the idea here is you basically have these variables, right. So, these are the variables that has to be make transfer, right. So, these are the variable, these are the input to the FU. So, I am just talking about the input FU. So, similar thing will come for input to the registers, right. So, for input to FUs, these are the transfer you have to make, and you have to make sure that this transfer is possible for a fixed set of say buses, right. So, what I can do by the formal formulation is that I can actually identify a variable bi if a particular variable vi actually map 2 buses, then it will be 1, otherwise it is 0, right. So, I can actually assume a Boolean variable bi if variable vi is actually mapped to bus, okay, otherwise it will be 0, okay. And then what is your objective? So, what I want to do, it is similar to the port binding problem, that I want to identify maximum number of such variable mapped to a fixed number of bus, right. So, I have given a fixed number of bus A, I want to maximize this value of bi such that maximum of such variable can be already mapped by to the fixed number of buses, okay. So, I want to maximize my score that bi. So, if bi equal to 1, that means that variable is already binded to these buses. So, that means if this summation of this total bi is maximum, that means I want to maximize the mapping of this variable to this fixed number of buses, but there should be some constant, right. So, as I mentioned that if you would in a particular state only in a time stamp one bus can transfer only one data, right. So, the total data transfer requirement of every state must be less than equal to of this particular fixed number of buses, right. So, how can I find out? So, this x I will say which operation is mapped to which timestamp. So, if I multiply this b I into x I, so that will tell me whether this bus transfer is happening in timestamp I L or not, right. So, for every timestamp the number of variables that get mapped and their transfer should be less than equal to the total bus requirement, right. So, that is what is given by this constant, right. This is for each timestamp. Okay. So, this actually formulate the problem. So, what it will do, if you give this to the ILP solver, what it will do? It will give you the total number of variable that can be mapped to this, the fixed set of A, right. So, it will just tell that, and then you can actually, if you just put that A equal to 1. So, that what it will do, it will try to find out all the variable transfer needed that can be mapped to one bus, right. So, this is how, if you just run it for say k iterations, you identify the minimum number of bus required also, right. So, you identify the bus 1, for which you identify what are the variable can be mapped to this bus, and then you remove those transfer. Then again you try to solve the problem for bus 2, you again identify the maximum number of variable transfer that can be mapped to those bus 2, and so on, right. If you just keep doing this, so you will identify the k, which is the minimum number of bus needed, right. So, that is something you can actually identify the solution to the problem 1, and for problem 2, what is already the problem it shows here. Okay. So, let me take the example here. So, here the variable is Z1, Z2, Z3, Z4, Z5, Z6, and I am actually discussing the mapping of this to the FU input. Okay. So, there are the buses at the FU input, right. So, what is here? So, this Z1 and Z2 need to transfer to this FU input in timestamp 2. In timestamp 2, the Z3 and Z4 need to be transferred to this to the FUs, some FUs, and this Z5 and Z6 is needed in timestamp 4. Okay. So, that means if the total number of buses is A, the transfer of this Z1 and Z2 must be less than or equal to A, transfer of Z3 and Z4 must be less than or equal to A, and transfer of Z5 and Z6 must be less than or equal to A in timestamp 4, this is in timestamp 3, this is in timestamp 2. So, for every timestamp we will have such constant, right. And now, if we know this value say 1, right. So, A equal to 1, then we can actually transfer maximum, so we have only one bus, right. So, every timestamp you can actually transfer only one data. So, then maximum 3 variable can be transferred. If there are 2 buses, so I can actually transfer all of them, because you can maximum transfer 6 data and there are 6 transfers. So, I can transfer all 6 variables, right. So, this is what this ILP formulation gives. So, I can utilize this ILP formulation to identify the minimum number of buses and also mapping of this transfer from this variable to the buses as well. So, this is one part, so which is basically the input of the FUs. The similar problem you have to solve it for the input of the registers as well, because there the problem is that this whenever you are writing this Z1 at the timestamp 1, this value Z1 need to be transferred to the register Z1. Right. So, from the FU output, so if this is say FU1, this is FU2. So, from FU1 to Z1 you need to make a connections. So, you have to identify which bus you will connect the output of FU1, right. So, this FU1 will go to, so this is the registers say. Okay. So, this will go here and there are fixed set of bus. So, you have to make sure that from FU1 you have to make a connections either to this register or this registers, so this bus or this bus. So, that you have to decide. Similarly, for Z2, because this is a Z1, this is a Z2, now you say this is your FU2. Okay. So, this FU2, this output also need to go to this Z2. So, you have to probably make a switch here and this to switch here. So, so that this connection can be made, right. So, you have to identify how many buses here needed to make sure this writing to these registers. Okay. And similarly, how to make this transfer from FU to those buses. Here the connections have to make from FU output to those buses. At the input of FU, the connections has to made from the registers to the buses and from the buses to the FUs. Okay. I hope you understand the overall problem of this bus based interconnection synthesis, and what is the optimization objective and how we can solve that problem. Okay. So, now I will move on to the controller synthesis part. In the controller synthesis part, so basically by this way you identify the say let us say this is a mux-mux connections, you identify the muxes and the exact connections, right. So, these are all identified and the registers, everything is identified, the muxes needed at the input of registers, everything is identified, right. So, what are the control signals is needed? We need a control signal for the enable of the registers, because it is not that all register will be updated in all cycle. So, you have to stop updating the registers by a enable signal. If the enable signal is 1, then in that particular control step that register will be updated, otherwise it will not be updated, right. So, you need this control signal for these muxes. So, you need control signal mux control, you need some control signal for the ALU, because this ALU can do plus minus greater than all operations. So, you have to tell this ALU which operation to be executed, and you need this and you need also control signal for these muxes, right. So, these are the control signals you need to do, and then if this ALU is doing say greater than less than, that greater than less than value 1 or 0 has to transfer to this controller, right. So, based on this value the controller state transition will happen. Okay. So, if C it will come here, say not C it will come here, right, something like this. So, basically once this data path is finalized, this is a very trivial task to identify the number of signals is needed and what is the value of those signals at each time step. Okay. So, let me try to explain with this example. So, here is the mux-mux connections we have obtained. So, let me understand how many signals is needed. So, I have first is needed the FU. So, here I have only one ALU. So, I need 1 bit, right. So, I need 1 bit. So, this is to say suppose doing plus and minus. So, these are all doing multiplication, right. So, I do not need any FUs control signal. So, I need 1 bit for FU, and then for this I need 1 bit, for this I need 1 bit, for this also I need 1 bit, for this I need 2 bits, 2 bits, for this also I need 1 bit, 1 bit, right. So, what is the total bit? 1, 2, 3, 4, 5, 9, 9 bits, right. So, I need 7 bits here, and I just put this is as a different thing. So, register mux in 2 bits. So, these are the 2 bits and there are 7 bits here. Okay. If there are 11 registers, for each register I need enable signal. So, I need 11 such bits, right. So, the total number of control signal is needed is 1 plus 7 8 19 21 bits. So, total control signal bits is 21 bits is needed. So, I can just analyze the circuit and I can identify the total number of control signal needed to make the control the data flow in the data path. Okay. So, then each timestamp you have to identify what is the value of these control signals. Let us say I want to do it for say timestamp 1. So, in this timestamp 1 these are the operations happening, right. So, the first bit is the FU. So, here say suppose this is say plus is happening here. So, I am just putting 1. So, say 1 means say plus. Okay. So, I am just putting 1 here, and for this these are the control bit corresponding to this mux in. So, since this is the first operations, all will take the left one, right. So, all will take the leftmost bit. So, it will be all 0 0 0 0, right. So, this is corresponding to 0 0 0 0, and then next 11 bits are basically corresponding to the register enable. So, in the timestamp 1 what are the operations getting updating? R1, R2, R3, R4. So, you have to put enable this 4 is 1 and rest will be 0 0 0 0, right. So, that is what I am done. So, R1, R2, R3, R4 is 1 and rest of the register enable is 0. So, that in the first control step only R1, R2, R3 and R4 data will be updated and rest of the register will not be updated here. Okay. And then here for this muxes, so this is the mux in 2 bits. So, for the first register the output is coming from mux 1, right. So, this is for register 1 it is coming from mux 1. So, I have to put 0 here. So, I am putting 0 here, and for this for R2 it is coming from M2. So, I have to put 1 here because 0 means FU M1 and 1 means FU M2. So, I just put it 1. So, that means in the control step 1 if I give this signal, it will make sure this data path is going to execute this behavior. Okay. So, similarly, in control state 2, I am going to give these signals and corresponding to set of RT operations going to happen. I am to do the same thing for all other states, right. This is how the controller will be synthesized. Okay. So, the summary of this controller synthesis is you identify the control signal first, you identify the control signal needed for FUs, you identify the control signals needed for the muxes, you identify the control signal needed for the register enables, you identify the control signals needed for the input muxes for the registers. Okay. And based on that, you first identify the total control width, data width, the control signal width, and then every timestamp based on the operation to be executed in that times in that particular clock, you identify the value of these control signals. And if you do this, you are done, right. If you do this for all state, your whole circuit is ready now, right. So, if you just complete this, you have a data path which is already synthesized, you have a controller which is now already synthesized. So, you will get this, right. So, your data path is this and this is your controller, you know how many states are there from the schedule behavior, and every time step what are the control signals is going to, you have to put it here, right. So, based on that, and then this value, this comparator value will come from this comparator unit, and based on that this particular behavior is going to execute the input behavior, right. So, this is what is going to happen, and this is what high level synthesis does. And it basically finally you have a data path, you have a controller, and then if these two work together, it will execute the exact behavior that we have taken as the input to the high level synthesis tool. Okay. So, this is what about this controller synthesis and this data path synthesis. So, I am going to cover now on little bit on this mux based interconnection optimization, which we have not discussed so far. So, in the mux based interconnections looks like it is very fixed, right. So, if you think here, I have already identified the multiple. So, you cannot change these things, looks like that based on the interconnection requirement, if there are 4 register input is coming to one FU, you have to put a mux size of 4, right, you cannot do anything. But there is a optimization possible here. So, let us try to understand this. So, suppose this is the connections requirement we have identified by identifying the operation that is going to execute in timestamp. For example, here this 1, 2, these 3 mention the time in the timestamp. So, that means in timestamp 1 I1 should come to this FU, in timestamp 2 R2 will come to here, and so on. Similarly, for the write input, similarly for this FU, right. Okay. So, you can understand here, and then also this 1 3 saying that in which timestamp this data will come to here. So, if I try to write the operation, so in timestamp 1 it is happening I1 in plus R3 and it is going to R2, right, for this FU, and for this FU it is M1 plus R5, sorry, this is multiplication, and it is going to R3. So, this is in timestamp 1, right. So, similarly, I can write for timestamp 2. In timestamp 2 it is R2, here it is R1, and the output is going to R5. So, R5 equal to R2, okay. And then similarly, here it is M4 star R4 equal to R1, right, and also there is a assignment here. So, basically R4 equal to R5. So, this is in timestamp 2. Okay. So, this is how I understand this is the schedule behavior, and based on this schedule behavior I actually identify these mass connections. So, you will tell me that you need a 2-bit control signal here, 2-bit control signal here, 2-bit control signal here, you will 2-bit control signal. So, my question here, can I optimize this circuit further? Okay. To do so, let us understand what can we do here, because this looks like very fixed, right. Let us try to look into these inputs, right. So, you can see here R2 is already here, right, and here it is happening R5 into R2. So, if you do R5 into R2 or you do R2 into R5, both are same, right, because it is a multiplication. But so, I can bring this R2 here, I can make this swap this connection, I can commute it, right, this is basically commutative, and R5 here, both are same thing, right. So, I can bring R5 here and I can bring R2 here, right. because this is the same operation, because in the timestamp 4 R 5 into R 2 is happening, whether it is R 5 into R 2 or R 2 into R 5, they are actually same, right. So, but doing this, what is happening here, I can see that this both R 2 here. So, I can reduce the one of the input, because it is still now it has become R 2 only, right. So, similarly, what I can do, I can bring this R 3 here and I 1 here, right. So, then what is going to happen, by this way actually there is a possibility that you might bring, so if you bring R 3 here, there are 2 R 3, right. So, now there are 2 R 3, there are 2 R 2. So, you can actually reduce the size to 2, because you know only you need R 3 and R 2, and what are the timestamp you need R 3, you need 1 and 3, you need R 3, and 2 and 4 you need R 4, and your control signal bit now will be 1 bit. Okay. So, that is what is the mux optimization, that you make the connections and then you check the commutativity of the operations, and based on the commutativity you can actually bring the common inputs of a mux into the same side, and as a result your size of the mux might reduce. Okay. So, if you just try to do this here, so what I have done here, I just swap this R 3 R 3 R 3 R 1, then this and also I just remove this R which I already told you, this R 5 and R 2, right. So, I have just swapped this R 5 and R 2. As a result, this particular mux has now only 2 R 3 and R 2 as the input. Similar things can be done here. So, if you just do this, you can see here that I can reduce this mux size into from 4 to 2, I reduce this mux size from this to this. So, this identifying this to this conversion is an homework for you. So, as a result, you can see earlier you are needing the control bit 2 bit, 2 bit, 2 bit here, 2 bit here. So, total 8 bits, here I need 1 bit, here still I need 2 bits, here I need 2 bits, 1 bit, right. So, I need 6 bits. So, I reduce the controller size as well as the mux size, because the mux size is also getting reduced. This is just a 2:1 muxes multiplexer, here it is 4:1 multiplexer. So, both the size of the controller will reduce and also the size of the data path will also reduce. So, this is how you can actually do the interconnection optimization in the mux based architecture as well. Okay. So, this is the final structure that I just talked about, okay, and this is the control signals which I already talked about. Okay. So, before concluding this discussion, I will also bring one more important aspect here, that this high level synthesis steps are interdependent, right. What does it mean? That you can understand that the kind of allocation binding is going to happen based on the schedule. So, if you have a different schedule, the lifetime of the variable will be different, and hence the register sharing will be different, right. Similarly, if your schedule is different, then the FU conflict will be different, right. So, and hence the FU binding will be different. So, schedule interferes the allocation binding result. Similarly, in the allocation and binding, there is multiple option of binding. So, if you just choose one, the corresponding interaction connection will be 1, and similarly, if the binding you choose a different binding, your interconnection will be different, okay, and the cost of the interconnection will also change. Okay. So, I have taken a very classic example here just to explain how this FU allocation binding and register allocation binding impact the interconnection cost. Okay. So, let us take this is my schedule behavior. Okay. So, here the variables are A, B, C, D, E, F, G and H. Okay. These are the 8 registers. Okay. And what is the lifetime? So, basically if I just draw it, so there are 2 timestamp, right. So, you can actually, so this A, B, C, D is here, A, B, C. A is needed here also, right, because A is needed here as well, and D is also needed here, right. So, this is your D, and then E is basically here, E and F is here, and G and H here. This is G and H, this is E and F, right. So, this is the time requirement, and based on the overlapping I can share the register. So, what I can do, I can actually map this B, E and G into one register? It is possible because B, E and G I just map into one register, and then C, E, C, F and H, which is possible because they have non overlapping time. So, suppose I put this B, G into register 2, C, F and H into register 3. Okay. And mapping of this operation, you can understand that O1 and O2 is happening in 1 and O3, O4. So, I just put O1 and O4 into this FU and O2 and O3 into this FU. So, this is the binding. So, if you just do this binding and you are actually performing the operation, you can understand that in the timestamp 1, right. So, timestamp 1, what the operation is happening? E equal to A plus B and then F equal to C plus D. This is what is happening in timestamp 1, and timestamp 2 what is happening? G equal to A plus E and H equal to F plus D, right. This is what is happening. So, to perform these operations, the interconnections will be like this. So, you can actually do this as a homework and identify these interconnections, and you can see here the total marks is needed 6 marks, right. 6 marks is needed, and out of them this is actually so these are all 2 bits marks, right. So, and the total 6 control signals is needed because all are single 2:1 marks. So, this is one possible mapping. So, because of this, because this register allocation and binding is not data path interconnections job, this is during allocation and binding phase, right. So, if in the allocation and binding phase the binding happen like this, your interconnections cost, if I just assume by marks and control signal. So, you need 6 control signal, 6 muxes. Okay. And then say based on this, so this is one another possible mapping is AG, B, CF. So, you can actually do this A with G, which is possible, then you do this B and E. So, B and E and then C and F, this is C, this is F, which is non overlapping, and then D and H, right. So, this is your D, this is your H. Okay. So, if you make these connections, this is a valid connections, and you can see here if and this mapping of operation is still 1 4 and 2 3. So, you do not need the input muxes, right. So, you still need the muxes at the input of the FUs. So, how many marks is needed? 4 marks and 4 control signal. So, your control reduced from 6 to 4, right. So, some improvement is happening. So, you can understand that same schedule, but different allocation and binding cost different interconnection cost. Okay. So, now let us move on to another form of thing. So, suppose you map this AG here, B here, same whatever you have done in the previous cycle, that AG, B, CF and DH, the same mapping I am doing register allocation AG, B, CF and DH, but what I am doing here, this O1 and O3 I am mapping to one FU and O2 to an O4 into another FU, right. So, this is the FU allocation binding change now, and for this if you can realize this operation here, you do not need any FU. So, your interconnection cost is 0 marks, 0 control signal, right. So, basically one thing is wrong here. So, you have to have a enable. So, this control signal corresponding to the register enable I am not considering, that is fixed for all things, right. There are 4 control signal for register. Here also you need 4 control signal for register, which is something is common. So, I am not considering them, right. So, here also 4 control signal for reg, because you need enable there. But you can understand that from the same schedule, because of the different register allocation and binding, my interconnections is actually changing and the cost is changing. So, and similarly if the schedule changes, your allocation binding will also change, and it can also impact the interconnection and binding. So, this is something is the interdependence of high level synthesis, and you cannot avoid it. This is how the whole thing works. Okay. So, probably once you do the scheduling, you try to if you just look ahead that your allocation, how it will impact in the allocation binding, that can be a good future study, right. So, you do your scheduling, make sure that your allocation binding will be smooth, right, your conflict will be less, something like this, or the way you do the allocation binding, you make sure that your overall interconnection cost will be less. So, this can be a good study that you formulate your allocation binding problem to make sure that overall interconnection cost is minimum, right. So, this is how we can actually formulate the problem, but the way we have discussed in this course we never thought about that, right. So, that can be a good future direction of research. Okay. So, with this I conclude today's class. So, in this class we basically discuss about the data path and controller synthesis. Although the conceptually the steps are very simple and it is kind of very conventional, but it is very important step. Without that we cannot realize the actual hardware, right. And also we have seen that this interconnection can be bus based and mux based. For bus based, your optimization objective is to use the minimum number of buses as well as the switch for the interconnections. For mux based, you try to reduce the mux size and hence the controller size. Okay. And then once you have this interconnection ready, your controller will be present by a controller FSM. So, in the controller synthesis, your objective is to identify the minimum number of control signals needed, and then every time step what is the value of those control signals, right. Once everything is decided, your RTL is ready, and if you just run that things in a using any simulator, it will exactly simulate the behavior which was given as the C input. Okay. And also we have also discussed one important point, that this high level synthesis steps are interdependent, and one decision of previous step might impact hugely the synthesis result of the next steps. So, one possibility of high level synthesis is that you make a that good allocation aware scheduling or interconnection aware register allocation binding, or this data path aware allocation and binding, right. So, that can be a good research areas. So, with this I conclude today's discussion. Thank you.